I guess that we are ready to start our first talk. I'm waiting just for Zuka Kakabadze, CEO of FUGO AI. Hello, Zuka. You are muted. Okay.
Thank you. Hi, Tomasz. Thank you.
Hello. So here with us is Zuka Kakabadze, CEO of FUGO AI, and he will be talking about very interesting thing especially for the technical point of view, how startups at the very early stage can embrace microservices. Welcome, Zuka. Handing over to you.
Thank you. Let me share my presentation. Okay. Okay. Oops. Okay, thank you very much, Tomasz, for the introduction. So, as a startup, when you're building a software product from scratch, the initial architectural decision you make will have long-lasting consequences. It's similar to building the foundations for a house. The wrong decision can come back and bite, hinder, or even break your startup. Hi, my name is Zuka. I'm the founder and the CTO of FUGO. And today I'm going to tell you about our journey as a SaaS startup and some of the key architectural decisions we made to get to where we are now. I believe the problems we encountered are true not only for startups, but any greenfield software project. To understand the decisions we made as a startup, you first have to understand the problem we set out to solve. 1 in 2 screens sold today end up not in people's living rooms, but in businesses like cafes, shops, and hotels. But the vast majority are not connected to a software and are managed manually using USB sticks or other DIY solutions. As a result, these lazy screens end up showing irrelevant and outdated content, and sometimes showing nothing at all. This is why we decided to build FUGO. FUGO is a digital signage content management software that allows businesses to create, publish, monitor, and measure audience engagement. At FUGO, our goal is to turn lazy screens into smart connected devices. Digital signage is an important part of any business, especially the customer-facing ones. It's a face of a company, and some businesses own hundreds or even thousands of screens in their network. So the responsibility you have there can be huge. Your system has to be strong and stable, because if it goes down, we can end up with a scene similar to the one we saw unravel at Gatwick Airport back in 2018, when flights had to be delayed for days because of a failure in their digital signage system. We already knew the domain problem pretty well, but building an innovative product is a risky strategy. Our solution had to find its own market niche, and this required testing a range of hypotheses about our users' needs and expectations by going through a rigorous build, measure, learn cycle. Once you find a repeatable business model, product market fit, you can then scale the product as fast as possible. Given the restrictions and business goals we had to make trade-offs when building our software. We summarized our main software goals into 3 main criteria. quick time to market. In order to validate our business idea within the budget constraints, we needed to release FUGO and reach users quickly. Extensibility. We had to iterate and release features quickly to meet customers' changing demands. Easy future scalability to avoid replatforming our entire system in 4 to 5 years down the line. Of course, this last point is only applicable if you're successful. Today, instead of telling you all the theoretical arguments for and against microservice architecture that will be comprehensively discussed during this event, I'm sure, I wanted to tell you instead the journey FUGO went on and why we opted to use the latest tools of the trade to build a hybrid microservice architecture with the help of Scalac. That is extensible, resilient, scalable, and fault-tolerant. Initially, I'm going to discuss FUGO's logical architecture and how we applied high-level functional architectural patterns to design a modular system. Then I will demonstrate how this looks in our code. And finally, I will show you how we mapped our logical design into a physical architecture, like microservices. So first and foremost, we wanted to align our software design goals with FUGO's business requirements. In fact, you might be surprised to hear that we didn't even discuss the idea of opting for monolith or microservice at the early stages. We simply wanted our logical architecture to be indifferent to the physical architecture. One of the goals of a good architecture is to define the various boundaries between containers, components, and modules such that when new requirements arise, as they will, the cost of change is minimized. With this in mind, we based our software design on functional architecture patterns. FP is well known for organizing code at the low level, but we can also apply FP principles to high-level design and architecture. This reduces complexity and improves the modularity of a system, whilst increasing testability and maintainability of an application. The good thing about functional architecture is that it automatically enforces high cohesion and low coupling without having to enforce team discipline. FP also gives you the ability to break down a problem into smaller, more manageable chunks that can be solved easily and then composed into a larger solution. The composition and abstraction gives you an ability to reuse your code and build new solutions from existing solutions. We will see examples of this throughout the presentation. One of the basic units of functional architecture, functional architecture is a workflow. By basic unit, I mean you can actually run an individual workflow if you want to into a standalone deployable container like they do in a microservice architecture. Workflows are built up using pure functions as independent units, containing only functionality they need. What's important is that workflows compose like functions do in a low level. From an architectural perspective, a workflow is a one-directional pipeline with inputs and outputs, as opposed to request-response model in object-oriented approach. The workflows we implemented in FUGO generally have a similar structure. It receives a command as an input, makes a business decision, transforms the data, and then produces new event as an output. So initially, we prepared UX designs for our software, describing FUGO's domain and core functionalities that software had to have in order to solve our users' problems. The designs clearly outline must-haves, good-to-haves, and future features on very granular level. why do we have such granularity? Well, we wanted to break down complexity and minimize the risk of change. For example, if we wanted to change the way uploading images works, it should not affect the way screens are paired. Every core feature from the UX design was translated into a workflow to kickstart our architectural design. As software engineers, our next task is to group these features or workflows into logical units. We used domain-driven design, DDD, to group related workflows into bounded contexts. DDD creates a shared mental model and aligns business and tech teams so that everyone is using the same terminology and the same words. This model is also present in the code. So let's break down a little further why context and why bounded. Within the context, we share a common language and the design is coherent and unified. By bounded, we want to reduce coupling between subsystems so that they can evolve independently. Autonomy is crucial here. Having autonomy means that the bounded context can make decisions without needing to wait on decisions or information from other bounded contexts. And if one goes down, it can continue operating independently. In order to avoid too many cooks in the kitchen problem, a bounded context should be owned by a single team or a developer. But a single developer can own multiple bounded contexts. So how does this relate to a physical architecture? So if the entire system is implemented as a single monolith, a bounded context can be as simple as a separate modules within a single container. Alternatively, each bounded context can be deployed separately in its own container, like in a classic server-oriented architecture. Or we could go more fine-grained and make each individual flow into a standalone and deployable containers, like in a microservice architecture. At this early stage, however, we do not need to commit to a particular architecture. The translation from the logical design to the deployable equivalent is not critical, as long as we ensure that the bounded contexts stay decoupled and autonomous. This is a simplified version of how we initially divided FUGO into bounded contexts using DDD principles. As you can see, the billing bounded context is independent from the screen bounded context. Some features might require multiple workflows from different bounded contexts. In this case, communication is achieved using events. Workflows within a bounded context are triggered by events. And an event triggering a workflow is actually a logical view, not a physical one. And this actually can be implemented either using request-driven command and control, which increases coupling, or event-driven queue using queues and message buses that decreases coupling, or a bit of both, like a hybrid version. If bounded contexts are not correctly created, you'll eventually you eventually turn your nicely decoupled architecture into a big bowl of mud. So how is code structured within the bounded context? The natural intuition is to use the traditional layered approach, where workflows basically go through every layer. This approach is problematic because any change in the workflow propagates to other layers and workflows. This architecture significantly reduces our ability to extend and iterate FUGO. Instead, we inverted dependencies and made it point inwards, following the functional onion architecture style. This way, the infrastructure code knows the core domain, but not the other way around. And I/O is kept at the edges. The the domain entails just pure logic and is isolated from the infrastructure. For example, a function that interacts with database is impure and therefore will not exist in the domain. But the core domain consists of abstract data types and pure functions that operate on these abstract data types. Types can be used to represent the domain in a fine-grained, self-documenting way. In many cases, types can even be used to encode business rules so that you literally cannot create incorrect code. You can then use the static type checking almost as an instant unit test, making sure that your code is correct at compile time. And this approach can actually increase your time to market, but it improves the reliability of your code, and any future changes can be rolled out with fewer tests and with greater confidence and speed. This is an example of what a workflow looks like in FUGO. We wanted our code to represent a pipeline. For example, when you publish FUGO playlist, the flow goes as follows. Get a playlist from a repository, send an event that says playlist is published, log that the playlist is published, and return the playlist. In our code, we have a function for each step. Each step needs to be stateless and without side effects so that it can be tested and reasoned independently. However, in practice, chaining functions into workflows is harder than it looks because the output of the one function does not match the input of the next function in the pipeline. And there are two reasons for this. The first is that functions have dependencies and extra parameters that are not part of the workflow pipeline. And the second is that they also have effects such as errors. And up until recently, actually, building such an architecture was unimaginable in a startup and required a considerable amount of acrobatics to achieve this. In order to build functional architecture, you need functional programming language. And that's why we decided to go for Scala ecosystem and Zio. We were attracted to using Scala because it is a powerful and expressive language with a strong type system. It allows us to reuse existing GVM infrastructure, which is important for startups as time to market is very short. And its concurrent and parallel programming tools allows for better utilization of the server resources, and as a result, smaller AWS bill. We combine this with Zio because it has a reusable and composable abstractions, and it gives us the ability to apply functional programming to our high-level design and architecture, and works surprisingly well with existing Scala and Java frameworks and libraries. It automatically makes the code base consistent and forces our developers to stick to FP, whereas other methods requires some team discipline. And one thing startups can lack is discipline. This is what our publish playlist workflow looks like in Zio. Zio library is centered around Zio type. Zio instance here describes effects that take an input and produces either an error or a desired value. So as you can see, Zio has three argument types. The input type R, which is an environment or a dependency. Output type E, which is an error. And in value type, which is your successful value. The publish playlist function sequentially composes all the sub-functions using for comprehension. The sub-functions themselves are Zio types as well. And if successful, the publish playlist function returns a playlist. If there is a failure at any stage in the pipeline, it produces a playlist error type describing the error. This function doesn't actually run. It is just a description of a workflow. To run it, you need to provide the dependencies. You can create dependencies in Zio using Z-layers. And Z-layers allows you to create services that then can be composed to build a graph of dependencies. The example above shows a playlist queue service API that lives in our domain layer. And below that is an SQS implementation of the playlist queue service. And this lives in an infrastructure layer. The graphs can then be injected into modules to make Zio Workflow runnable. For each bounded context, we then construct dependency graph and inject them into our Scala module, like shown in here. These modules are either run as separate microservices or as a modular monolith. And in a modular monolith, Z-Layers actually allows you to share dependencies across modules to save resources. For example, an HTTP client pool. In order to run our publish playlist workflow, you need to provide the layer graph as shown here. So after completing our logical architecture, we need to consider technical requirements and map logical architecture to a physical one. Each FUGO bounded context or module has different requirements in terms of scaling, availability, or behavior. Currently, we have 8 microservices running on AWS infrastructure and 1 modular monolith called FUGO CMS. FUGO CMS is deployed as a modular monolith because initially it was not clear which workflow would require scaling. Each module in the monolith has its own DynamoDB table and SQS queue that can scale with the module if we want to. We put them in a monolith because microservices can have operational overhead, but you can actually mitigate this by automating the infrastructure and using cloud services to their fullest extent, like using infrastructure as a code, Kubernetes or Fargate in our case. And this allows you to then concentrate on the business code and spend less time on the infrastructure code. On the other hand, we knew that the router module, for example, that coordinates screens, needs to be a singleton and be deployed as a separate microservice. And the separation between the FUGO CMS and the router was obvious because they have a completely different scaling requirements. And we don't want the performance of router to affect our user experience, and we don't want FUGO CMS to affect the screen functionalities. So monolith or microservice, what should you choose? Well, it's not a black and white choice. It is more a spectrum, which you can consistently shift if you use the logical architecture that we presented here. And as mentioned, one point in favor of using workflows as the unit of design is that they can be physically deployed in any number of ways. For example, as a modular monolith, a microservice, or even as an independent serverless function. So ultimately, the decision has to come from your use case. But either way, I would strongly recommend using a functional workflow architecture, as it gives you a lot of flexibility whether you want to run your system either as a monolith initially and then shift towards microservice, or if you want to deploy microservice straight away. Well, that was our FUGO's journey. Thank you so much. And if you have any questions, I'll be happy to take.
Thank you very much, Zuka.
Thank you.
Thank you. Yeah, I'm trying maybe because we are waiting for questions from the main chat, but let me ask this question, because you can still name your company as a startup, as I understand. So do you think that having this approach at the very early stage gives you more advantage competing with your, with your colleagues from the other startups? Or because when I'm talking with startups, they are trying to build something as fast as possible, as quickly as possible to just, prove product market fit. Your approach is a little bit different. Your focus, because you are from the engineering field. So do you think that this makes competitive advantage, this approach that you use in your startup?
Yeah, thank you, Tomasz. It's an interesting question. I think we have to define at what stage startup is, and what sort of resources they have. I mean, if they're at the very, very early stage and they're just like very limited budget and they just want to try something out, maybe you might not even sit down and spend any time on architecting anything. But if you maybe like raise your seed funding and you want to like build a product, I believe today's frameworks, programming languages, and infrastructure automation tools allows you to spin up really high quality systems that you don't need to rewrite in the future. So you do need to have some certain level of expertise, and I guess that's when you guys come in. If a startup lacks a certain a certain scale, then it's a good example for Scalac to step in and guide that, because eventually the benefits down the line are very clear. And for me, for example, for our case, what we noticed was that having a high quality product from the get-go was very important. This gave us confidence to speak to not only small clients but big clients as well, and sell them our service. And we knew that our product is not bullshit, it's not going to break. So I think it does give you an advantage.
Okay. We have one question, as I see from our audience. It's a technical one. Hi, workflows are Zio-specific approach? This is the question.
No, it's not. It's functional programming specific, but we used Zio to implement them. Before, it was quite hard to use workflows in a different programming language, or using you needed a lot of functional programming skill and training. But Zio allows you to apply build workflows without even kind of understanding functional programming, or you don't even need to be an expert in functional programming. So
okay, thank you very much. Okay, that's all of the questions. So, okay, another one. Okay, waiting for the question. Okay, let me read it. So that was a great explanation of all the constraints in your designs. And we see the question. I will be interested in more details about techniques for building a modular monolith.
So, as I explained, we initially split up our system into bounded contexts, and then we deployed these modules as a single container. And if you're familiar with Scala, that you can do using SBT. And then in the future, if we find that one of the modules requires scaling because the usage is going up, then we can very easily just change some code in Terraform and dissect our modular monolith and separate it into a separate container. I mean, if you want to kind of go into more details, I'm happy to. I will share my contact details after the presentation, and I'm happy to discuss it as well.
Thank you very much. We will follow up if the question will be need more explanation. Okay, so thank you very much, Zuka, for your time. It was
Thank
a
you.
pleasure having you today. All the best with your venture.
Thank you.
Within the next talk, we'll start in. Okay, there's one more question. I see. Let me. Okay. Okay, we have it. What would be the difference between using Zio and using the Lightbend microservices tooling, such as Lagoon?
Yeah. I don't really have much experience with Lagom, but I believe Lagom is based on ACA technology and Actor systems. So as I understand, Zio is more functional. It uses more functional programming principles. And yeah, I think they're both good. The one thing that I can say that Lagom is probably quite good with when it comes to distribution, but I don't know. It's I don't think they're even comparable, because one is more like a framework, and yeah, I don't have much experience with Lagom, so.
Okay. In a couple of hours, we will have a speaker from Lightbend, so maybe we can discuss also this later. Yeah. So then, thank you once more, Zuka, for your time.